So we've said before that temperature is one of the factors that affects the rate of a reaction. And in this session, we're going to talk a little bit more about collision theory and how that helps us understand the ways in which temperature changes the rate. So if we're picturing what the molecules are actually doing during a reaction, then in order for a reaction to happen, the molecules have to collide with each other. And so the rate of the reaction is going to be dependent, proportional to how many times the molecules collide. So picture them, you could start to picture them like balls in the ball pit, and they're all like, bouncing around, or popcorn in a popcorn maker. And they're bouncing, and sometimes they hit each other. And so we need to have more collisions in order to have more reaction, to increase the rate of the reaction. But in order for the reaction to actually happen, the collisions must have the right orientation and enough energy. So not all collisions successfully result in the formation of products. If we think about this reaction between NO2 molecules, we see that in order to make NO and NO3, the molecules have to line up right so that during the collision, that O atom can be transferred from one molecule to the next one. And so we can imagine drawing what we call a transition state, where we have the reactant molecules and the product molecules, and the transition state is where the system sort of stops being reactants and starts being products. So we see that the transition state is sort of suspended in between the reactants and the products. So in order for this transition state to form, the two NO molecules have to be arranged correctly in 3D space so that the oxygen atom can transfer, and they have to bump into each other hard enough so that that oxygen atom can actually be transferred. So imagining this reaction where NO2 reacts with carbon monoxide to make NO and CO2, which of these reactants have the appropriate orientation to react? The best answer here is C, because the NO bond matches up with the carbon, so that way when those collide with each other, they can interact and make the CO bond and break the NO bond. You might have also considered answer D, and that's not a bad choice either. I think that C is a little bit better because the atoms are lined up more head-on. And also, if we were to think about resonance structures, the resonance structure where we have the single bond is a little interacting with the C is a little bit more favored compared to the double bond, because it's easier to break a single bond than it is to break a double bond. So molecules can react when they collide with correct orientation and sufficient energy. We're going to call that energy requirement, we're calling that the activation energy. So the activation energy is the energy required to make the transition state in order to convert reactants to products. And we can represent this transformation of reactants to products using a potential energy diagram like the one shown here. This is potential energy. So on the y-axis, we have energy, and on the x-axis, we have something called extent of reaction. And so extent of reaction is a little bit abstract, but basically we have reactants on the left side going to make products on the right side. And so we can represent the energy required to make the transition state as the energy difference between the reactant energy and the transition state energy. And then the energy, so that reactant activation energy is the energy of the collision that has to happen in order for reactants to become products. That is different from the delta H, or the change in energy or enthalpy of the reaction overall. So the enthalpy difference between the reactants and the products can be shown by looking at the difference in energy levels there, and so we get delta H. So delta H, we'll see, is a thermodynamic quantity, while energy of activation, that is a kinetic quantity. That's going to control how fast the reaction goes. So you try. What would be the activation energy for this reaction? So we measure the activation energy difference by looking at the difference between the starting energy of the reactants and the energy of the transition state, the top of the curve. So the difference in energy there, going from 100 to 20, would be 80 energy units. So how do activation energy and rate work together? So the activation energy is that energy requirement. Activation energy does not depend on any of the other factors like concentration or temperature. It is just a feature of a particular reaction. And so if we imagined, so in this graph, we're imagining that there are some molecules that have a particular kinetic energy. So the y-axis is number of molecules, so how many things have the specific energy that is listed on the x-axis. And so we can see that a lot of molecules have this kinetic energy in the middle. So the most molecules have that kinetic energy. However, the kinetic energy required in order to make the products, the activation energy, might be higher up here. And so only the molecules that have at least the activation energy or higher, which can be represented by the area under the curve above the activation energy, only those molecules can react in order to form the products. Now, if the activation energy is lower, like say the activation energy for a particular reaction is only here, now all of these molecules have sufficient energy in order to react. And so if more molecules have enough energy, that means the reaction will happen faster. So a reaction that has a lower activation energy will be faster than a reaction that has a higher activation energy. And we can represent that using this distribution of the number of molecules. So let's think about this graph. So here we have distributions of molecules at two different temperatures. Which of these temperatures is higher? The higher temperature is temperature 2. So temperature 2 is greater than temperature 1. How do we know that? So we can see that at temperature 1, the range of kinetic energies is smaller. So there are fewer different kinetic energies. Whereas, and we can see that the average is a little bit lower than for the temperature 2. At temperature 2, we have a greater range of possible kinetic energies, and we see that the average is a little bit higher. So maybe you remember from Chem 131, or if not, you can hear it now, that a higher temperature means a higher average kinetic energy for the molecules. So at the higher temperature, those molecules have more heat energy, more motion energy, and so they're bouncing around more faster, and they can hit each other harder than the molecules that are at temperature 1. So, for a particular reaction, we said that the activation energy is fixed. And so here, for this particular reaction, the activation energy is this energy, this level. And so only the molecules that have that energy or greater can react. And so we see here, if we look at the area under these two curves above the activation energy, we see that temperature 1 has sort of this much area, but temperature 2 has all of that and more. So we see that the area for temperature 2, the number of molecules that have the right energy, is greater for temperature 2 than temperature 1. And so thinking about what the molecules are doing and the fact that they're able to make more and harder collisions at higher temperature helps us understand why the reaction is going to be faster at a higher temperature.